Um, yeah, so my name's Garrett Nobis. I am a second year graduate student at the University of Arkansas, and I'm going to be talking about temperature, albedo, and emissivity of ice giant moons from Voyager 2 data. Um, the Neptune system results were just published in Planetary Science Journal last month, and we have begun working on some of the Uranian moons as well. So we don't understand the surfaces of many icy moons particularly well. And for a lot of them, Voyager 2 is the only spacecraft to visit them. It flew by the Uranian system in 1986 and the Neptune system in 1989. And if we could constrain these surface properties, it lets us do things such as comparative planetology, it informs models, as well as future outer solar system missions. And I guess pictures here, Titania is on the left and Miranda in the middle and Proteus on the right. Okay, so how we're going to look at it is with Voyager 2's iris spectra. So this is a far infrared spectrometer that took spectra from the 200 to 900 per centimeter wave number range. And I'm just going to very quickly go over how we select spectra because there doesn't seem to have been a previously established way to determine what is a good spectra. So one is that we need the spectra to be on the day side so that we have signal. And the other is that we need this, the thing that we're looking at to be entirely within Iris's field of view. So this is a lot of words in math, but basically what we're doing is just setting up a geometry problem where you have the spacecraft, the distance to the thing that you're looking at, the radius of the moon, and the radius of, or the size of Iris's field of view. And so we define this beta value here, and this lets us make a condition that if met, the spectra is good. And we find that we need this X value for some of the moons, and it varies between moons, and this is probably due to surface properties. For instance, Proteus is very dark, and therefore you need a much higher X value to still have a good spectrum. Okay, so there's that. Now we want to find temperature. So we're going to use the Planck function here. And the important thing about it is that the temperature is going to depend on emissivity. Furthermore, I told you that the spectra are from the 200 to 900 per centimeter range. But as you're going to see, the spectra are quite noisy, and we actually need to constrain that further because there's lower signal to noise at larger wave numbers. So this is what the Triton spectrum looks like. So again, we are only caring about that 200 to 350 wave number range when we are making our fits here. This is an average of 66 spectra, and we get a temperature of 37.9 plus or minus a half Kelvin. And this agrees nicely with the original iris analysis calculation with 16 spectra, so that's good. We also did this for Proteus. Proteus only has 4 spectra that are enough of a quality to use. And for that, we find a unit emissivity temperature of around 47 Kelvin. Moving to Miranda, we performed our fit with an average of 4 spectra, and we get, for unit emissivity, a temperature of 64 Kelvin. And this is quite a bit off the maximum temperature that the original Miranda analysis found. And the reason for this, there's a couple of things here. There's one, when Voyager 2 went by Miranda, it was summer solstice for Miranda and Titania, meaning that the temperature that were taken are the maximum temperatures. They're the hottest that things get. But the reason our value is so low is most likely because the emissivity is probably quite a bit lower. And as you see later, by lowering the emissivity, we'll be able to rectify the difference there. And titania, we have 7 spectra. They were not previously looked at, and we get a very similar unit emissivity temperature as for Miranda. Okay, unit emissivity temperatures are nice at all, but we want to actually put constraints on the actual temperature and emissivity and albedo. So how we're going to do this is we're going to make a plot with emissivity on the x-axis and temperature on the y-axis. We are then going to take this Planck function that I showed you earlier, and we're just going to plot it over a bunch of different emissivities. That's going to be our data curve. And then alongside that, we're going to use this Stefan-Boltzmann law, and we're going to pick an albedo that's been predetermined from the literature. And we can make this sort of gray body temperature curve. And wherever our data intercepts with one of these gray body curves, that gives us a combination of surface properties that could exist for our moon. So what does that look like in practice? So for Triton, plot here, like I said, emissivity on the x-axis and brightness temperature on the y-axis. The black curve is our data. That's just taking that Planck function and just doing it over a bunch of different emissivities. All the colored curves are just some sample gray body albedos. So wherever one of those intercepts the data, that is a possible combination of albedo and emissivity and temperature. Now, we're pretty sure that the bond albedo of Triton is somewhere between 0.8 to 0.85. Other presentations have displayed this as well. And so if we assume that, we could set a lower and upper limit on temperature and emissivity, which turns out to be somewhere between 40.5 to 46.5 Kelvin for temperature, and an emissivity somewhere between 0.2 and 0.5. All right. Now, for Proteus, we don't have any of these values predetermined to anchor our results to. So what are we going to do? Well, we can make a pretty rough estimate on the surface properties of Proteus because we know that Proteus is very dark from visual images, and the only place that these low albedos intercept the data is over there at the high emissivity end. So if we assume the emissivity is pretty close to 1, the temperature is going to be about that unit emissivity temperature I showed earlier. And the bond albedo might be roughly around 0.2. It doesn't intercept the 0.1 bond albedo. It may be darker in reality, but this is sort of the best estimate that we can get for the data because we don't have any of these values to anchor to figure out the other two. Okay, so for Miranda, once again, it's gonna be like Triton, so we have a pretty good idea of where the bond albedo sits, and this again will give us a temperature and emissivity range. Again, these temperatures are the maximum temperatures because this is being observed during the summer solstice. And as you can see, it varies quite a bit, 10 Kelvin. That's because these values are all very sensitive to bond albedo. They're all very sensitive to each other. So even a little bit of uncertainty in bond albedo there gives us quite a bit of uncertainty of temperature and emissivity. Titania, I should say 0.17, not 0.16, but has a very similar bond albedo, and it turns out that it also has a very similar temperature and emissivity to Miranda. And this is perhaps not too unsurprising, as at least visually, the two worlds are very similar. They're both dark and perhaps have similar composition. Okay, so what can we draw from this? So for Triton, we have an idea what the composition is. And since we know the surface properties, we can make specifications on the composition. So for instance, laboratory experiments that have been done, our values of emissivity and temperature are consistent with a beta nitrogen ice with a grain size of about millimeter. For Proteus, we don't know what the composition is. It's made of spectrally neutral dark stuff. So unfortunately, the best that we could say is it's probably something different than the ices that we're seeing on Triton and Pluto. And as far as Miranda and Titania, we're just starting this analysis. But Oberon, while we don't have spectra for Oberon that are good, it does have a very similar bond albedo, so it's not too much of a stretch to say that it probably also has similar surface properties to Miranda and Titania. But what we really need are missions to these ice giant moons, because we're not working with much here as far as the spectra goes. But I do hope to continue this sort of analysis with Iris to the other moons that it took spectra of. There's 5 Jovian moons that have various degrees of how well they were looked at, and as many as 25 Saturn moons have spectra, and I say at least half of those have not been analyzed at all. So part of my PhD has just been going through and looking at these spectra and see if there's anything to find. And I like to acknowledge the people that helped me learn how to read and navigate this data set. It's certainly been a challenge given how old it is. But yeah, with that, that's all I got.
Very cool, Garrett. It's nice to see this old data set getting turned into useful science. We have time for questions.
Choose me. One of the questions I had when I was looking at this is where you're looking at extremely cold temperatures, and one of the things we've seen on the Saturn satellites is that emissivity might change with temperature. Is that something you've looked at all? I appreciate it adds an extra variable, and you might not have enough information to constrain it. But have you thought about emissivity variations with temperature in your models?
We haven't, and the problem is, like you said, we're just so limited on how much we can actually extract from these spectra. I mean, and especially since like I gave the error the temperature fits, but emissivity is very sensitive to temperature, and I can't really. It's hard to constrain it anymore than what I have here.
Okay, let's catch up later. But yeah,
okay,
yeah, cool.
We have time for additional questions. So I have a question. Garrett, did I understand, are you assuming that or taking the whole disk that you're seeing to have the same temperature, or is there a variation in temperature across the surface?
It's a brightness temperature, so it's just an average temperature of the disk. Yeah.
Okay, John, and then Casey.
For Triton, did you try and look at spectra from the lower albedo regions as separate from like on the south polar cap?
Right. Unfortunately, this is sort of just a spectra of the whole disk that we're seeing. So it's just everything in it's everything in the disk. So unfortunately, I can't really differentiate between the albedo regions with these spectra.
So that was just a choice you made in your analysis, is where Triton basically filled the beam.
Yeah.
Okay.
Very nice talk. Did you see any trends in albedo, excuse me, emissivity and temperature with distance from the host planet?
Can you speak up? Sorry.
Did you see any trends in the temperature and emissivity from Uranus? As you go farther out, does it get hotter or colder or lower or higher emissivity?
Sorry, could you speak up one more time? I'm sorry.
Maybe you can help.
I think Casey is asking, as you go further from the planet, so Miranda, Ariel,
right.
That's Earth, Umbriel, are you seeing any kind of trend with distance as you
go? Unfortunately, so for the other 3 Uranian moons, I don't have good spectra. So all I have is Miranda and Titania. And Titania and Miranda seem to be quite similar to each other. And if there's differences. It's too subtle for me to see with this data.
Okay, thank you.
All right, let's please thank Garrett one more time.